Good morning, mathematicians. New day, new episode. You might have noticed I've slowed down on video production. Also, I don't know, I gotta be honest, I kind of feel like taking a break from live streaming for a bit. We'll see. I just lately have been feeling like, I should wake up and do math immediately. Hello, Deepak. I mean, of course I do math on stream, but, lately I've been feeling like, I just want to wake up and, sit in silence with, a book and do some work. So we'll see. There might be a break from streaming soon. Hello, Daysen. Hello. Where are we going today? Maybe I'll talk about a graph, a cool kind of graph that I learned about recently. I proved something about. I hope by the end of the summer I can tell you guys about these mysterious graph things I've been thinking about. They're called Paley graphs. And basically what you do is, so you take a finite field of order q, some prime power, where q is congruent to 1 mod 4. And now you define a graph so that the vertex set of your graph is fq. And then your edges, so xy, will be an edge of this graph if and only if x minus y is a square. And so it turns out that this graph is strongly regular. So that means that not only is it regular, so every vertex is incident with, so you're strongly regular with parameters, I don't know the usual parameters. I think it's like n, k, mu, lambda. So n is the order, k is the degree that every vertex has. Mu is the number of common neighbors of two adjacent vertices. So if x and y are adjacent, then they have, say, mu other common neighbors. That's basically the number of triangles. And then lambda says that if two vertices are not adjacent, then they have lambda. So this would be lambda equals 2 lambda vertices in common. So this graph is strongly regular, and it is also vertex transitive. What is its automorphism group? Well, I can tell you generators for its automorphism group. We have maps. Some more direct construction practice has been done. Practice contrapositive. Good. Glad to hear it. Glad to hear it. Glad to hear you're making progress. So here are some automorphisms. So given A, which is a square, a non-zero square. So, sorry, that should be x, non-zero square. And B, anything in here, we have the map TAB which will send x to ax plus b. How did he come up with this graph? I don't know. That's an interesting question. I mean, it's kind of a natural thing to consider, actually. You actually, technically, you don't need this condition, but you only get a directed graph because this is symmetric. Yeah, this is, symmetric. X minus y is a square if and only if y minus x is a square. If q is congruent to 1. Hello, Marigold. But if q is congruent to 3, then you only get one or the other. So it'll be a directed graph in that case. But I think in a certain sense, like, it's kind of a natural thing to consider, right? I mean, if you care about graphs and you care about numbers, like, right? It's just about basically writing down nodes and putting edges between them if they're equivalent or not under some way. And so, there's probably a lot of different interesting ways one could, a lot of different graphs that arise this way, but probably, I don't know, like a lot of equivalence relations you do this with or something, like maybe they're just, or it's not quite an equivalence relation, but they probably end up being other commonly named graphs, and these ones just happened not to be. I mean, I think this is a pretty natural condition to consider, to be honest. Not saying that I would have come up with this, but it's, I don't know, not the craziest thing, in my opinion. Your proofs are reviewed by your Discord friend, has a master's degree, you think. Okay, well, that's good. That's good then. So it sounds like you've got someone who presumably knows what they're doing and is giving you help with proofs. Good to hear it. That's true. Graphs are very common everywhere. Well, maybe not everywhere, but I do love graphs. Right. So I claim that all of these are automorphisms, and that's almost it. And Frobenius. And that's it. Those are all the automorphisms of these graphs. And let's see. Bring up some pictures from Wolfram. Yeah, here's some pretty pictures of the Paley graphs. The 5 cycle is included. What's this paper? Is this history? Maybe this will give us insight as to how or why he came up with these things. Interesting. Okay, so here, interesting. Neither of these papers cited uses the concept of graphs. So that's very interesting. Yeah, I think it's just a coincidence that it's similar to the Lee group wiki picks, though. I mean, I think that's just a consequence of, like, if you put enough nodes in a circle with a bunch of edges between them, all graphs will look the same. So I don't think there's anything deeper going on there. Speaking of graphs, can L packets be visualized in terms of graphs? I don't think so. Yeah, Descent is related to graphs. But I don't think there's any graph theory way to talk about the Langlands correspondence. Present how these strange ideas came about by explaining the background to these two papers. Oh, nice. Nice. This Paley graph has a very nice, this is a very nice drawing on the torus. Oh, that's another thing we should talk about. Maybe I already said this a little bit, but yeah, I mean, I would, well, research group eventually maybe, but yeah, when you look at Paley graphs, does it really look like those fancy E6, E7 lattices? I don't think so. I think it's just coincidence. One of the few papers that look readable. Yeah. I mean, I would I do want to read more about Descent at some point, but I also feel like there's a number of other reading groups that I should sort of want to form that are maybe more directly relevant to things I need and want to do. Yeah. So let me mention something though. So probably people here have heard of the concept of a planar graph. So that is a graph that can be embedded without crossings. Of course, that doesn't mean any way you draw this graph that it will be without crossings, right? These two graphs here are isomorphic. But I haven't done anything silly though. Hang on. Let me do this. Let me write it this way. Right? But so these two graphs are isomorphic. There is not a vertex here, right? That's just an artifact of the drawing, but it has a crossing. But we know there is at least one way to draw this graph without any crossings. Meanwhile, famously, the complete graph on 5 vertices does not. There is no way you can draw this so that the lines won't intersect. Finish proofs. You might join a research group with me. Well, that'd be the dream. Super long term. Just have a massive research group born out of this community. Not sure if there's a concise way of defining an equivalence relation on a graph. Yeah, well, there's lots of different ways. I mean, it's just like if you take like literally you can define an equivalence relation on any set, right? But then the question is there a sort of is there a nice equivalence relation that can be defined, right? So like a group, you might want an equivalence relation where like that respects the group operation, right? So like if G is equivalent to H and X is equivalent to Y, then G X will be equivalent to HY, for example, right? And there's lots of ways to do this. Actually, so here's one of my favorite things. I guess I'll just say this in words because it's hard to draw a dodecahedron. But if you take like a regular embedding, so you take a dodecahedron, but you put it on like a sphere, and you have all the points sort of like equidistributed, right? So you've got this like spherical dodecahedron, and you just think about the edges. Don't worry about the faces. Just think about the edges and the vertices, and then you take the antipodal map that identifies opposite points on the sphere. So X gets identified with minus X. Then the corresponding graph, you get a well-defined equivalence relation, And the graph that you get is the Peterson graph, which is, of course, is one of the famous Moore graphs I was talking about. And so you do get this like quotient of the Peterson of the, like you get the Peterson graph as like a quotient of the dodecahedron in this way. Have I seen Kontsevich graphs? No, but I'll look that up right now. Good morning, Nicole. Morning, Nicole. Kontsevich graphs. KS. The graphical representations of calculations in deformation quantization. Interesting. Directed graphs with specific rules how to associate with mathematical expressions. Yeah, I guess maybe the wiki has something. You think this is a more natural graph? You think this is a more natural graph than Paley graphs? Or are you talking about the Cayley graph comment? Yeah, the Pearson graph is amazing. I've heard people lots of times say, yeah, if you think you have a conjecture about graphs, test it against the Peterson graph. It's a conjecture breaker. Kind of off topic, but you were wondering if I had any recommendations for self-study algebraic geometry. Well, Ravi Vakil now has a hard copy of his Peterson graph. Yeah, Peterson graph is very natural. There's so many cool ways to build it. Here's a net. It's also a special class of graphs. So here's what you do. You look at the you take all what is it? I think I could be getting things backwards here, but you take all 2-element subsets. You take all, no. Wait, 5 choose 2. 5 choose 2, 5 over 3 over 2. Right. Yeah, so it's all, I think, 2-element subsets. So your vertex set is going to be all 2-element subsets of the set with 5 elements. And then I think you say that A is adjacent to B if and only if, I could be getting it right. I think maybe it's like their intersection is empty. It's either that or it's like their intersection is 1 or something like this. I don't remember, but it's this is the general idea. And then you get the Peterson graph. It's another really cool way of building it. But yeah, Vakil does a crash course of category before he gets into the beef of algebraic geometry. Yeah. So you could skip some of it, but you will need some of it. I guess it also depends, Marigold, on your background and like what have you already seen. Like, have you done any differential geometry? Have you done any category theory? Like, how strong's your algebra and your modules? All of those questions kind of inform, because if it's like no to all of those, then I would probably, recommend you a different book that starts you off just with like very, very basics of algebraic varieties, or going through something like a Tia McDonald that just teaches you some algebra, but there is like a little bit of affine schemes right in the beginning. Whereas, I don't know, if you know a bunch of like category theory already and you have like geometric intuition from other things, then like, yeah, Vakil's book is a good thing to go for. Oh yeah. Anyways, I was gonna say, so okay. So there's this concept of planar graphs, and then there's this concept of, and then here we have like the complete graph on 5 vertices. But what if we tried drawing a graph instead of on the plane? What if we try and draw a graph on a torus? Does that change anything? Well, let me make a map of the torus here. So let's see. These are identified. These are identified. And let's see if I can do it. It might take more thinking, but I'll see if I can just freehand it through guessing. So if we do this, now I need to, I basically have two more things to draw. So I can't draw across this way, but what I can do now that I'm on a torus, I could go around this way, and that line comes out here, boom, and that's drawn. And then I also need a line here. So I guess if I went like this, boom, that pops out here. And then I can go here. And then finally, I guess I can go this way. And that line pops out over here. And then I can turn up here. And then there we go. I've drawn the complete graph on the torus in such a way that the lines don't cross. So it turns out that you can take... you can draw a graph, even though you can't draw a graph without crossings in the plane, you might be able to draw a graph without crossings on some surface if you put enough holes in it. And in fact, that's a theorem. Any graph can be drawn on just a compact 2D surface if it has enough holes in it. And so naturally you can ask, what is the minimum genus that you can draw, that you need to draw a given graph on there? So for K5, we know that the minimum genus is 1. You can also ask the same thing, but you could try and do it on a Mobius strip. So there's also like a notion of like unorientable genus. And it turns out, by the way, so the known Moore graphs are the 5-cycle, the Peterson graph, and the Hoffman-Singleton graph. And it turns out that the non-orientable genus of the Hoffman-Singleton graph is 57. Ooh, spooky. Very spooky. Why do I say that's spooky? Because the missing Moore graph is supposed to have degree 57, and the total number of cycles in this Moore graph is 57. Somehow I always come back to yapping about this. You've done a T.M. McDonald. Oh, okay. Well, then I would say Vakil and homological algebra. Wow. Yeah, I would say go read Vakil then. Definitely, that's the book to go read. Yeah, I mean, free PDF. Don't be intimidated by the fact it's like 800 pages. You know, just read the parts that you want to read. He's you know, he puts a lot of things throughout where he's like, oh, this exercise is essential but boring, or like this exercise is really fun but not important, you know. So believe him when he tells you those things. But you should definitely get it. Yeah, free PDF, or there's a really nice hard copy that's been printed. I haven't pulled the trigger on buying the hard copy, but I might soon. I did buy that book some people have told me about, The Invitation to Representation Theory, through polynomial representations of the symmetric group. Am I going to get as much out of this book now as I would have like 5 years ago? Probably not, but I'm like, it'd be a nice read, and it was only like $20, you know? The damn Springer ads on the internet, you know, on like chess.com or whatever, like the algorithms got me figured out. And I'm like, I'm sorry, $20? I can't not buy this book. That's insane. There was a number of other $20 books that were looking mighty fine, but I stopped at that one because I have a problem. Wow, my coffee doesn't feel super warm. I need to drink more than I yap. Question for anyone. Is there a sort of recommended order to study pure math? Yeah, yes and no. in terms of a hierarchical sense. You just graduated and want to get into it. Well, congratulations on the graduation. Graduated high school then, and you want to get into like university level pure math, just so I understand. I mean, there's some things you want a foundation in. Certainly, like, something you'll want to start with is proofs. Like, this is the big hurdle. This is the big transition from Dwrensha books are great. They've got lots of cheap books that are good. Right? The concept of proof. So you'll want to do an introduction to proofs thing. University. Oh, you graduated in mathematics. I'm a little confused by your question then. You graduated university in mathematics, but you want to get into pure mathematics? Or you graduated with, sorry. I just don't know the best way to answer your question because I'm a little confused where you're coming from and where you want to go. Like, is it that you did applied math and now you want to do pure math? Sorry if I'm being dense here. Good morning, Ken. Good morning. Z has an exam coming up on representation theory. Nice. And you're really struggling with just understanding the notation. Do I have any tips? Well, that's interesting because when I think of subjects with cumbersome notation that I find confusing, representation theory isn't one that comes to mind, but that's just my personal tastes, I guess, or upbringing. Yeah. I mean, I guess one answer is to just do a lot of exercises, which I know is a sort of a blanket answer you always give. But I guess if it's a lot of symbol pushing, like when I think about differential geometry, I think about a lot of symbol pushing and stuff that I didn't always understand. But sometimes just pushing through and doing a bunch of exercises. Yeah, it could just be could just be it's not clicking for you for whatever reason. I don't know. Are there like particular? Well, you said it's a notation thing. Like, are there other more particular are there other particular aspects of representation theory that you're finding confusing? Like certain concepts that you're finding confusing? Hey, the other day I was plugging Sage Math and doing stuff on CoCalc. So I would highly recommend go play around. Like, you can have it like spit out character tables for you and stuff. So I would recommend that. That might help you because you can have it like compute things for you, and then you can ask your own questions and test stuff. So I don't know. Maybe that's one way to go about it. Maybe I'll fire that up in a second. But Paul Maurice remembers getting homological algebra by Cartan and Ellenberg a few years ago. Under $5. Damn, really? $5. That's a steal. Wow. Yeah, differential geometry has some pretty bad notation. I mean, I do like differential geometry, but let's be real. The notation's pretty nasty. I don't know if I hate MathFrac. There's times when I love it more and times when I love it less. Do I know about the Deligne-Ilusi proof of Kodaira vanishing? I don't. Let's look it up. Maybe this is just the statement here. I don't know if it's going to say what the proof looks like. But we've got some other questions in chat, so maybe I'll come back to this in a second. Mostly applied, I see. But you had one class on group theory, very basic, and you did your final project on category theory. Oh, interesting. And you want to learn more category theory specifically? Or just more math, pure math in general? So I would say then... I mean, at this point, like the most rudimentary thing for you to have down is just a basic introduction to proofs, and it sounds like you have that. If you had, even if it was very basic, it sounds like you already have that from a group theory course. You probably already got that from some of your applied math courses as well, and certainly doing a category theory project. I mean, reading a book. So I'm sitting in on a reading group that some undergrads are organizing at my university for category theory, and we're going through Tom Leinster's notes. And that can be a good way to also, so if you want to learn more category theory, I would go read something like that, but also sort of the advantage of category theory is that you see the connections between different fields of mathematics. So that book can actually be a great jumping off point, right? Because he might bring up some example from homotopy theory or something. You go, oh, I've never learned homotopy theory. That's fine. Don't worry about that example. I mean, category theory works in such a way you might even be able to understand something about that example without knowing stuff about homotopy theory. But then that could serve as a source of inspiration for you. You could say, wow, that seems like a really cool thing. Let me go crack open this book on homotopy theory or something. Now, of course, there are certain subjects that depend on others, right? Like, you're not going to do advanced representation theory, for example, unless you have basic linear algebra or something like that, right? So there is kind of a dependency structure, but there isn't like... I don't know. It becomes easier later on once you have a foothold, and it kind of seems like you do, to jump around. So yeah, I don't know if that gives you a sense. Follow what you want to do, follow what interests you, and just sort of as you go, backfill things, right? You start reading about some subject and all of a sudden they're going on about modules and you're like, oh, I don't know anything about modules. Well, okay, I guess I better go read up about modules a little bit first, something like that. Reading Lee's book and have to go back and forth to definitions. Yeah. Yeah, it's definitely involved notation. Yeah. I don't know. I mean, I feel like, I don't know. It's just kind of the way it is, though. Never got over using superscripts for vector coordinates. Oh, wow. And never got used to Einstein summation either. Yeah, it's a good thing to get used to, though. You want to hang out with your physicist friends sometimes, presumably. I mean, you got a Hilbert picture, profile picture after all. Yeah, the Einstein notation thing can be nice. Maybe I'm okay with it because earlier on in my mathematics journey, I was inspired by physics. So maybe I got used to it early or something. Is it normal to have learned or have been exposed to a lot of math that's not on your recorded academic BG? I don't know what BG is. I'm guessing your transcript or something. But yeah, I mean, I would say that's pretty normal. You should strive to do that. Yeah, I mean... Yeah, I feel like that's the difference between having a math degree and being a mathematician, basically. It's like you just show up to your classes and learn what you have to do for your classes and then leave. And it's like, okay, do you even care? Yeah, you should be reading stuff on your own time and going to talks and seminars and things like this. Would I say I have a greater appreciation for what category theory is trying to do once you learn a lot of other diverse mathematics? I would say that that's the case. And I think that's what makes learning category theory difficult. Not because it's actually difficult to do the proofs or something. Like, they're all pretty, like, you can just unfurl the definitions, and like it's not any harder than like a first course in group theory at the basic level. But it's, easier to understand, like, to just immediately see like why a group might be interesting. Oh, symmetries. Oh yeah, I want to understand the ways I can change this object with having it look the same. Whereas, category theory, again, it's one of the purposes it does is to highlight similarities between entire branches of mathematics. So if you haven't seen a lot of branches of mathematics, it's not going to be very meaningful to you. That being said, I mean, we'll see. It's early in the summer, so, retention, you never retain 100% of people in the reading group. But for this reading group, there's definitely some people who are much earlier on in their mathematics journey, learning category theory. So we'll see how they do. Maybe, I don't know. Emily Real has this dream that, one day we'll have refined both our axiomization and our pedagogical approach to infinity categories so much that it'll be an undergrad topic. Yeah, that's been your experience. Lots of examples of category theory. Obviously reference other topics that you have no idea on. Like, you worried if you can jump straight into something or not. Yeah, I mean that's entirely up to you. Like, some people seem to be fine in the abstraction, and but I think for most people, myself included, I like to have examples to lean on. And yeah, it will be tough because there are a lot of examples. There's a lot of examples that are either kind of just like, they're cute and they're fun, but it's like, okay, is that useful? Like, I've got these shorts, a couple shorts on my channel about the category of integers under division, and how GCD is a categorical product, and the Fibonacci sequence is a functor, and things like this. And it's super fun. That's why I made shorts about them. But also it's like, but like, who cares? It's like, it's a cute little thing, but like, okay, is that what category theory is doing? So like, there's these cute little things. There's tons of examples like that for you, but then it's also like, okay, you probably want an example that's like, yeah, but like, when am I actually going to use this? And then, yeah, unfortunately that is just, requires a lot of stuff. So I would just keep on keeping on if I were you. Like dig into a category theory book. Doesn't have to be Leinster, but dig into a category theory book. Go as far as you think you can, and if you're really like, okay, if there's like certain examples or topics that are just coming up so much, and you're like, this example is coming up so much, I really just feel like I need to go read it. Then, pause, or simultaneously like go and read this other, read on that other topic. But yeah, I mean, the best way to figure out is just try, right? Just try. Go keep reading some category theory and see. Maybe you'll be fine. Maybe you'll be fine with it, and you'll sail right through, and you'll be like, yeah, you know what? I didn't even need those examples. I don't know. Category theory opens up your brain. How little we were in high school or undergrad. Hello, Luna. Yeah, but you know what? I mean, I guess, but category theory never made me feel like this. You know what made me feel like this? Homotopy type theory, which I guess you kind of need category theory for, but homotopy type theory made me feel like this. So, yeah, calculus was a research topic once. That's true. It is crazy. Yeah. This is something that we forget. Like, it's so easy now to teach Galois theory, group theory to undergrads. But like, there was a time when this was like groundbreaking, difficult things to grasp. You can teach different sizes of infinity to high schoolers now. And the like best mathematicians in the world had like violent arguments over it. You know what I mean? Like, yeah. So I don't think it's that crazy to think that one day infinity categories could also be like your first proofs course or something. Is that going to happen anytime soon? I don't think so. But, what the hell do I know? You think a lot of times trying to learn new math can be difficult. Yeah. Part of it is because you'll make mistakes. Yes, but that's also essential. That's how you learn. And you have to be mature enough to know that. Yes, exactly. And you have to know when to look for help. Yeah. You're taking math proofs and you're cooked. Well, not John Cena. Exactly what John Cena would say if he was in my chat, not wanting people to know that he's being cooked by proofs. Welcome to the channel. Feel free to ask me questions here in my office hours, or as you might have seen, I have videos, a series called Your Proofs Are Trash, and another one I was trying to get started called How to Prove It. But I haven't felt the motivation lately. And I don't know if people missed at the beginning. I've been feeling lately a bit like maybe I might even take a break from streaming for a little while. Possibly. I don't know. We'll see. I said that, and then, I started drinking coffee, and I started talking, and I was like, this is fine. How far on your journey should you start trying to read new publications? Any advice on how to start? I mean, I say the sooner the better. Like, start trying now. Of course, if you're trying to read like the latest papers in categorical Langlands, it's probably not going to happen, right? Whereas like, I don't know, there's more papers on like recreational number theory, probably that's pretty easy to read and get into. I remember reading Ravi Vakil's advice when I was in undergrad, and he was like, subscribe to get email updates from archive as soon as possible, and just go and read the abstracts and just get a sense of what people are doing in the field. I mean, I tried doing that, but I don't know. Then you get too many emails in your inbox, and then you get paralyzed by it, and yeah. So, but for example, like I did a research project in my undergrad, and the first part of that is all just reading papers. And I also did a reading course in my undergrad where, again, we just sort of read the sort of foundational papers on like the Fiedler vector in spectral graph theory. So, I mean, I would just go to archive and start, just every day or every couple days anyways, just type in, I don't know, say you're interested in group theory or something. Just search group theory, and okay, you'll get stuff like this does not look like it's actually group theory, right? But just look at what people are doing. And okay, probably, if you just took your first course on group theory, like none of these are going to make any sense to you, right? But like, just sort of look through, read the abstract, see there's some words, right? You're like, oh, hey, CELO, I learned something about the CELO theorems, right? Stuff like that, right? Yeah. I mean, also, you could maybe ask, if you're interested in a particular field, maybe ask professors at your university or people online and stuff like, hey, what are some good papers to read? Like, I'm early in my journey or something, or just tell people where you are in your journey and be like, hey, I want to start trying to read research, like, and some, maybe those papers will be papers from the 70s or something, right? So you'll have to start, but eventually you'll get closer and closer to nowadays. And hey, I mean, there's research level papers nowadays that are probably readable for you as well, but like those aren't going to be maybe as well known, so maybe not as easy to track down. Ken, that is such a fun fact. That is a super fun fact. Wow, we don't even know if that's a homotopy group of a sphere. That's amazing. Do we know? Are there? Oh, I'm interested as to like what non-theorems we have about that and whatnot already. Like, what negative results do we have, or positive results do we have? Like, are there non-constructive ones where like we know Z mod 2 shows up as a factor infinitely many times, even though like we can't say precisely which spheres or something? Found Harvard student GitHub, and he took category theory, algebraic topology, and algebraic geometry, and it was 2 semesters of each. Got demotivated. Yeah. There'll always be people infinitely better than you. That's but if you're a true addict of math, that at the end of the day, it won't matter. Yeah, I don't know. A good analogy for doing proofs is it's like looking for a needle in a haystack where there are tall stacks of hay and the needle you want to find is golden. Yeah, well, I don't know. I don't know if I necessarily agree with that. Depends on the proof, right? I guess maybe research is more like that. But even then, I feel like there's certain questions that are just very natural. It's like you just sort of follow your nose, you apply standard techniques, and the answer comes out. Yeah. First semester of research is learning about MATLAB, learning about the field you want to study, dynamical systems, using a book you and your professor agreed upon. Yeah. Making sure you understand the definitions and the basic outline for some of the proofs. Yeah. It's good to take your time. And to play. Crunch lots of examples. Do lots of basic examples. And slowly build them up more generally. Yeah. Wow, what is this? This is a hell of a title. Constructions of metaplectic representations of SL2. Is that supposed to be over the ring of integers mod 2 to the n? Non, je ne parle français. Je mange à putain de Québécois. Je ne parle français. I'm going to Quebec City though, in like a week? What the hell? A week? Oh shit! I need to. Oh man. I need to book. I don't know. Hotels are expensive. I guess I'll stay in a hostel. I thought about using couchsurfing.com. I used to use that when I was in my undergrad and traveling for conferences and stuff. How to sub to archive? I don't remember. It's been so long. But if you just go to the main site, there's some way to do it. Or, I don't know, ask Google or the Google AI. It'll tell you. I gained a lot of personality with French. Yeah. I feel like you do. Okay, here's I'm not a language expert, but I've tried learning a couple languages here and there. And here's what I think. Maybe call this controversial, but I feel like in order to have delivery with the language, I feel like you almost need to take like the caricature of the language in almost a mocking sense and try and put that on. You know what I mean? Because like if you just try and like deadpan, like normally deliver a different language, of course I'm starting from a base of English, so just translate this to whatever English you're in. But you deliver it with the same, like, I don't know, English attitude, I feel like that it will fall flatter. And so, like, sometimes, like, when I'm practicing, like, when I was practicing German or Italian or Spanish or French, you know, I sort of had in my mind sort of this, like, caricature, you know, the stereotype, you know, I almost imagine, like, when you try and do an accent of that language in English or something. And I feel like that helps, I don't know, put you in the mentality or something. So, no, I have not read EGA, SGA, etc. I have not, no. Sometimes picking out the right idea or the right way to formalize the idea is the tricky bit. MATLAB is great for helping visualize dynamical systems. Maybe. I mean, no, I shouldn't say maybe. I shouldn't disagree with you at all, I'm sure. Qual è tu teorema favorito? Mi teorema favorito es ich habe keine Ahnung. No yo soy favorito. Yeah, I don't really have favorites. I don't know. That's not entirely true. I've on my personal webpage, I have a list of ideas. I have a list of ideas and theorems that I like, and some of these I've turned into shorts, and eventually I'll do more. But I don't know. Favorites like doesn't make sense to me. Like I could never pick a favorite movie, for example. Never. I'm like, first off, I couldn't even pick a favorite genre because like I need all of them to do different things for me. And then within each genre too, I could never. Am I getting comped by my university? You mean for YouTube? Absolutely not. I mean, I get my stipend. Oh yeah, Delina Lucy. Well, I'm about to end the thing. I'm sorry, Paul Maurice. But Paul, you keep asking me about cool stuff that I don't fully understand. You know, I know enough to understand the basic statements. Yeah. And one of these days, I know I'll oh, I almost forgot. Okay, before I go, here's the list of here's the list. Maybe I'll try to put this in the description of the video. This is the list of Twitch streamers who do math. Physics and Depression, amazing. What an amazing title. So yeah, I guess I will. I haven't checked it out yet, but I'll have to dive into that. Why do they have to use fancy words on archive? Because math is fancy. Not sure about negative results for homotopy groups of spheres. The calculations are more or less done one by one. Yeah, I figured. I thought maybe there would be some general things, but yeah, maybe not. It's just hard. It's just a hard problem. Okay, I'm out of here, gang. I gotta go prove stuff. You gotta go prove stuff. You know how it is.